Welcome back to Calculus 2, Section 6.3, Taylor and Maclaurin series. We're going to make a definition of the Taylor and Maclaurin series, talk about Taylor polynomials, look at the remainder theorem, and finish the section by showing that Taylor and Maclaurin series may be used to represent functions. Let's get started. Let's start with some notation. Beginning on the left, we have a pair of open parentheses which contain a binomial, the difference of variable x and constant a. The vertical bar is used to represent evaluated at, and then as a subscript, we are indicating where the variable x is to be evaluated at. This is just fancy notation for the notion of plug in x equals a. When doing so, you come up with a minus a, which you easily recognize is 0. Let's do that again. Now here it's a little bit more complicated in that you want to read from left to right. And in reading from left to right, you first come upon the derivative operator, d by dx. I've highlighted it in a white box to say that you first perform this operation. Mentally, we can do that. The derivative of a constant, mentally we can do that. The derivative of the variable x is 1. The derivative of a constant is 0. And evaluating a constant for the variable being a, well, it's just going to be the constant, which we know is 1. And then one more. Same notion that now we have two derivatives, but we know that we're taking a derivative of the constant 1, which will be 0, and a constant evaluated at the variable x equaling a will just be the constant again. Nice. All right, so how is that going to be so useful to us? Well, we have a function f, and then we can write down a power series to represent the f, that we have the power series centered at x equals a. Equivalently, this notation, power series notation, can explicitly be written out, and we can investigate each term individually. Well, when we evaluate the expression on the left, and if our notion is that we want the left-hand side to be the same thing as the function, then when we evaluate the expression on the left at, for example, a, that we would expect, noticing on the right, that that's plugging in x equals a, all of these binomials will go to 0 when we let x equal a, that the right-hand side will just be c naught, and the left-hand side we have this notation, evaluated at x equals a. And again, if we want this expression to be the function evaluated at a, then what can we do for c naught? Well, we should set c naught equal to the function evaluated at, the input being a, and we have much simpler notation, just f of a. So c naught should be set equal to f of a. Okay, so we're going to build on this pattern that what we've done is we've walked through the idea of considering 0 derivatives on the function, and then for this power series to have any chance of representing the function, which is a function of x, that at least when we evaluated a, that this power series evaluated at a should agree with the function evaluated at a. Let's record this. So we've done the 0th derivative case and found that the coefficient C0 in this power series needs to be f of a. So let's move on to the first derivative. And again, we want this left-hand side to be the function. So what should happen? Well, let's investigate. Take the derivative of the left-hand side is the same thing as taking the derivative of the right-hand side. Well, we know that a derivative of a constant is 0. We have nothing to record. Move on to the next term. The derivative of a linear function is just 1. Therefore, we pick up the coefficient C1. However, the next term has a coefficient on the binomial to the power 2. By the chain rule, we know that the power 2 is going to come down, and the power 2 will be decremented to 1. Thus, under a derivative, this term becomes twice the coefficient C2 multiplying the binomial x minus a. Pause for a second. What will the next term be? Well, it's going to follow a very similar fashion. We're going to take the next term, which will now have a power 3, bring that down to the front. The 3 is going to match up with coefficient C3, and that power 3 will be decremented down to 2, and so on and so forth. Now, what is it that we want to do? Well, we want the derivative of this expression at least evaluated at a. Here's the derivative of that expression, at least evaluated at a. Well, what are we going to get? We can investigate, plug in a for x. All these higher order terms will go away. We'll be left with just C1. What should this be set equal to? Well, if this is representing the function, this would be f prime, and then f prime evaluated at a. Thus, C1 should be f prime at a. So we record that, and now we have the first derivative case. And we move on, looking at the second derivative case. In a similar fashion, we know that a derivative of a constant is going to go to 1. And a derivative of a linear is just going to give us a coefficient. But notice that the coefficient here is twice C2. Taking the derivative of the quadratic term, we'll get the existing 3 times a 2 times the original coefficient C3, and so forth. Very nice. Same thing. If we want the power series to represent the function, then 2 derivatives on that power series evaluated at a. What will it give us? Well, again, we're plugging in x equals a. Therefore, we'll only produce the constant term, which is twice C2, that this should equate to 2 derivatives on the original function evaluated at a. 2 derivatives, original function, evaluated at a. More simplified, that's f double prime at a. Nice and easy. Solve for C2. Find that C2 should be f double prime at a over 2. Excellent. So we have infinitely many more that can be done. Let's quickly walk through the next one. The third derivative, same notion. Constants go to 0, linears go to just the coefficient, and so forth. Note that, and then plug in x equals a. Doing so, note that 3 times 2 is the same thing as 3 times 2 times 1. Notation for that is 3 factorial. Left-hand side, 3 derivatives on the power series, which we want to represent the function. Thus, having free choice of C3. Let's choose C3 to be f triple prime evaluated at a divided by 3 factorial. Nice. All right. So that's the first 4 terms. And if we want to expand out and try to notice a pattern, I mentioned the notion of a factorial. Here we have the first 4 terms. Let's introduce factorial notation. 0 factorial by definition is 1. So f of a is the same thing as f of a divided by 1. 1 factorial is 1. So f prime of a is the same thing as f prime of a divided by 1 factorial. 2 is the same thing as 2 factorial. 3 times 2 is the same thing as 3 factorial. Observe the pattern that if we're looking for the ith coefficient, that we're taking c sub I to be the ith derivative. So this is the 0th derivative. Here's the first derivative. Here's the second derivative. Here's the third derivative. The ith derivative evaluated at a divided by I factorial. All right, let's recall a little notation again. So this is power notation. The nth derivative, we can use brackets on the integer and in the subscript, the superscript. And this is the nth derivative of the function. And then here on the right-hand side, we have Leibniz notation, dn by dxn of a function. This is the nth derivative. So coming back to where we were, the nth coefficient in a Taylor series will be given by the nth derivative evaluated at the center a divided by n factorial. So that's pretty nice. You want to put a big star on this and memorize this form, the nth derivative at the center divided by n factorial. That's the nth coefficient. And having that, we can now make our definition of 2 things: the Taylor series as well as a Maclaurin series. What's required? We need a function which is good, extremely good. What does that mean? The function has derivatives of all orders at this center a. We need to be able to differentiate the function as many times as we like and be able to plug in a to the derivative. So let's look. We have a series beginning with the index at 0 going out to infinity, c sub n coefficient, the nth coefficient, on the binomial x minus a raised to the nth. And the nth coefficient is the nth derivative of the function at a divided by n factorial. All right, so here is a definition with 2 things being defined: the Taylor series, which has an arbitrary center, and the Maclaurin series, which has always the center being 0. Good. A Taylor series is unique. So if f has a power series at a that converges to f on some open interval containing a, then that power series is the Taylor series for f at a. So this is something that we want to arrive at. And let's see how we can make that happen. Or in other words, this is the big question of this video. Does the Taylor series for f at a converge to the function f of x? Right. It'll take a little bit to digest this question, but I think we'll get there in the end. Okay, So we've made the definition for the Taylor and Maclaurin series, their power series. Their definition relies on knowing the nth coefficient. We need functions that are super nice. We can take as many derivatives as we please, in fact, all derivatives. And the difference between a Taylor and Maclaurin series is that the Taylor series has an arbitrary center A, and the Maclaurin series is always centered at 0. Okay, so the big question was, does the Taylor series converge to the function? The function is the function. We can work with the function all day long. Something else that we can work with all day long are polynomials. So we want to put in our hand the function, and then put in the other hand a polynomial. Now, the polynomial is going to be called an nth Taylor polynomial or an nth Maclaurin polynomial. And as before, the only difference is where is the center. If the center is arbitrary, then it's a Taylor polynomial. If the center is 0, it's a Maclaurin polynomial. Now, the nth Taylor polynomial, the n is indicating the degree of the polynomial. We went over the nth coefficient c sub n takes the form of the nth derivative at a divided by n factorial. And therefore the ith derivative is the ith derivative of the function evaluated at a divided by I factorial. If we want the nth Taylor polynomial, we consider all terms up until the nth term. All right, let's do an example. So here's the definition again, and here is our example. We're going to take the function, the natural log of x. We're going to use as the center a equaling 1. And in this example, we're going to compute the first 4 Taylor polynomials. The Taylor polynomial degree 0, degree 1, degree 2, and degree 3. So how do we do that? Well, we have the definition here at the top of the screen. And p sub n is a polynomial. It's made up of n plus 1 terms. So if we want the 0th polynomial, we need 1 term. How do we get that term? Well, we look at the function and evaluate the function at the center. Our function is f, and our center is 1. F of 1, that's f of x being ln, f of 1 is 0. That's pretty easy. So for the k equals 0 term, we come up with the 0th Taylor polynomial to be 0. Nice. So now that we have the first term, if we're next going to look for the first Taylor polynomial, we simply have to add in 1 more term. So how do we get that term? Well, we know that we're now interested in k equaling 1. So for k equaling 1, we want to find the first derivative of the function. ln of x differentiates to 1 over x. And then you plug in that function at the center a. 1 over 1 is 1. Thus, f prime of a is going to be replaced with 1. X is x, and a is 1. Nice. So here we have the first Taylor polynomial for the function f with center x equaling 1. Good. Move on to the second Taylor polynomial. Means we should add in a quadratic term. So we're going to have the binomial x minus 1 quantity squared, and we need to figure out its coefficient. To figure out the coefficient, we need the second derivative. That means differentiating the first derivative. X to the negative 1 differentiates to negative 1 over x squared. Plug in 1 for x, get negative 1 over 1 or negative 1. So we look back at the first Taylor polynomial and now add in the degree 2 term. So we'll come up with x minus 1 and then negative 1 over 2 factorial multiplying x minus 1 quantity squared. Very nice. For the k equal 3 term, we can look here at the k equal n term. We know that we want to compute the third derivative, negative x to the negative 2. We need the negative 2 to come down, producing a positive 2 as a coefficient, and negative 2 as a power decrements to negative 3. Evaluate that at 1 to get f triple prime at 1 equaling 2. And note that when we plug in, we're going to have a 2 in the numerator over 3 factorial. 3 factorial is 3 times 2 times 1. That'll simplify to 1/3, so that we're going to add in 1/3 x minus 1 quantity cubed. Beautiful. So these are the first 4 Taylor polynomials for the function f, taken to be the natural log of x, with center 1. Nice. So go ahead and consider this assignment where you match graphs with functions. And the idea here is to note as the degree goes up, the better the ability for the polynomial to approximate the graph. Okay. And then here is a little bit of scratch work for you to do. Repeat our example, but for a function f taken as 1 over x squared. Nice. Okay. So the exponential e to the x will play an important role. The exponential e to the x is actually very easy to work with in this setting. And that's because the exponential e to the x is its own derivative. That means that all of its derivatives is just the function e to the x. And if we consider the Maclaurin polynomial, then that means we're using center a equals 0, and e to the 0 is just 1. Nice. Well, when we plug all this in, we're going to get 1 for f of a. F prime of a is 1. X minus a is just x. F double prime is 1 over 2 factorial. Let's look down here. So 1 plus x plus 1 over 2 factorial on x squared plus 1 over 3 factorial on x cubed. Now we have the pattern plus ... plus 1 over n factorial on x to the n. So note that by stopping at some finite power n, we have a function which is perfectly well defined. What are we looking at? We're looking at the nth Maclaurin polynomial for the exponential e to the x. The big question in this section is, does this nth polynomial, for the degree getting larger and larger, turn into the function e to the x? All right. Well, we can motivate that notion by looking at the first few Maclaurin polynomials for e to the x. The red graph is the exponential. And here is the constant 1, the 0th degree polynomial. Here's the first polynomial, the second Maclaurin polynomial, the third Maclaurin polynomial, the fourth, and the fifth. So note that as the n value gets larger and larger, the better and better the polynomial does at approximating the function. All right, so that's good motivation. Here's that big question again. Does the Taylor series for f at a converge to f? So do these Taylor polynomials become the original function? That's the question we want to answer. Okay, so we've done the Maclaurin polynomial for e to the x. Let's find the Maclaurin polynomial for trig function sine. What does this involve? We need to take derivatives. We need to take infinitely many derivatives. Luckily, there's a pattern to be observed. If we look at the first 5 derivatives, the 0th through the 4th derivative, start with the function that's just sine of x. Sine differentiates to cosine. Cosine differentiates to negative sine, and we know that sine goes to cosine, so negative sine goes to negative cosine. But one more derivative is going to bring us right back to where we began. So we only need to look at the first 4 instances, k equals 0 through 3, and then copy and paste to get successive instances. Now, because we want to know a Maclaurin polynomial, we take all of these functions and evaluate them at 0. Sine of 0 is 0, but cosine of 0 is 1. So the pattern is 0, nothing is there, to positive, back to nothing being there, and then to negative. And then that pattern repeats and repeats and repeats. Let's plug this in. So here's the form that we want to plug into. This is just the nth Maclaurin for any function f. And then we're going to use our particular information here. So the very first term, there's nothing there. It's just 0. So the 0th polynomial is 0. And then the next one is just 1 times x, or just x. After that, we have a 0 coefficient, so there's no term there. It's a non-zero term. And then we switch to a negative term. Okay. We also have the 4th derivative, which evaluated at 0 is 0. So let's add in the 5th Maclaurin polynomial. All right. Okay, so now we're going to get a little bit notationally heavy. So let's try to understand this notation. We're going to introduce I equals 0, I equal 1, I equal 2. And what I is doing is it's counting by 2 terms. Collect 2 terms, I equals 0. Collect the next 2 terms, I equal 1. The next 2 terms, I equals 2. So we're counting in blocks of 2. If we come back and we think of just counting term by term, starting with the first term, but letting that be the 0th term, the k equals 0 term, k equal 1 term, and so forth, that whenever k is even, we have a 0 term. Or only when k takes an odd value is the term non-zero. So now we can associate the k with the blocks of 2 variable I, and we can relate k to I in the form of twice I plus 1. So if I is 0, 2 times 0 is 0, plus 1 gives you k equal 1. If I is 1, 2 times 1 is 2, plus 1 gives you 3, and so forth. All right, so why do we need to do that? Well, take a look. When we count by blocks of 2, and we look at the odd powered term, that we have also the pattern of plus a positive coefficient to a negative coefficient, and then back to a positive coefficient. Or in other words, when the I variable is even, we have positive coefficients, but when the I variable is odd, we have negative coefficients. So observing that, we can then consider -1 to the I. So if I is even, -1 to an even is going to give us a positive coefficient. And then we can next account for denominators. Here we have 1 factorial on the bottom, 3 factorial on the bottom, 5 factorial on the bottom, which is k factorial, and then k factorial, and then k factorial. But we know that we can express k as twice I plus 1. So we come up with a twice I plus 1 quantity factorial in the denominator, and then that is exactly the power appearing on x. Okay, so that's quite a bit involved for something that started out so simple, but this is what we have. Something to help you remember this form is to think of the sine wave, its graph, and try and think, is that an even function or an odd function? Because it passes through the origin, we know that sine is an odd function. It has symmetry with respect to the origin. And that here in its Maclaurin polynomial, only the odd indexed terms, the k being odd, are non-zero. All of the even indexed terms are 0. All right, so this is something that you want to put a big star on and memorize. Good. All right, so here's a fun little Desmos assignment. Sketch the sine wave, that's already done in red, together with the Maclaurin polynomial for n's from 1 out to 51. And here's what it should end up looking like. Nice. And as we saw before, we had an exponential graph, and the blue polynomials, as you took higher and higher degrees, better and better approximated the original curve. Same thing's happening here, which is, again, begging that big question. Do the polynomials, if you take them higher and higher degree, will they converge? Will they recover the original function? All right. Make sure you do this assignment where you repeat exactly what we did for coming up with the Maclaurin polynomial for sine, but start with cosine. And hint, cosine, when you sketch it, has symmetry with respect to the y-axis. It is an even function. All right, find the explicit form for the Maclaurin polynomial is 1 over 1 plus x. And that is Taylor polynomials. To find some machinery to answer a big question, we're going to need Taylor's theorem with remainder. If we think back to series, that studying the convergence of a series was studying the convergence of a sequence of nth partial sums. Having nth partial sums, we can easily define remainders. Power series are very much like series. So coming up with remainder for a power series is very similar. That the nth remainder on a power series will be defined as the function minus the nth Taylor polynomial. Okay, so the big question is, do these guys, p sub n's, as n goes out to infinity, do they become the f? Well, that is tantamount to the remainder tending to 0. For this to become that, their difference must become small. That means that the remainder needs to go to 0. Pretty straightforward. We're going to come back to that straightforward, simple statement after we do this computation. Let's look at the assumption we're going to make. We're going to take a function f, which can be differentiated n plus 1 times, on an interval, capital I, that possesses the center A. P sub n is the nth Taylor polynomial of f at A that we've been studying. And then taking the difference, we'll let that be the nth remainder. All right, that's the assumption that we have. Now we're going to start a proof. And in this proof, what we want to do is we're going to treat x as not the variable, but a fixed point. So this is a constant. X, pick x in the interval. And instead of x being the variable, we're going to introduce a variable t. And we're going to use that function t as an independent variable to a function g. Here's the form of g. Looks rather complicated. It's actually not too bad. How can we understand the g? We can understand it first by looking at what would it be if t were a. Well, this g would exactly take the form of, look up here, the nth remainder is the difference of the function and the nth Taylor polynomial. Move the nth remainder over to the other side. Doing so, you would naturally have 0. And g at a is exactly that expression of f of x minus the nth Taylor polynomial minus the nth remainder. So this is naturally 0. Now with that in mind, knowing that p sub n, the form of p sub n, looks very much like this f of t, f prime of t on x minus t, f double prime of t over 2 factorial on x minus t quantity squared. This is essentially p sub n, except that the center a has been swapped out with t. Okay, good. Now, this is the form of g. Take g and plug in x. Remember that x is a constant. When we plug in x, for t, we're going to get x minus x is 0. X minus x is 0. The very first two terms, f of x minus f of x is 0. And x minus x is 0. Thus, g of x, g is a function of t, g evaluated x is 0. Okay, so the point here is that we've come up with a function g which agrees at a and x. Something else to note is that g, as we've defined it, is a sum of f and a polynomial in t. Since our f is differentiable and a polynomial is infinitely differentiable, g has n plus 1 derivatives in t. Okay, so that's going to be important for applying Rolle's theorem. But first, we want to consider taking a derivative of g. Since g has lots and lots of terms, and a lot of the terms take this form, let's look at taking a derivative of a term of this form. Well, what is this form? Well, essentially it's a product. And since we want to differentiate with respect to t, k factorial will be a constant. We have something in t times something else in t. When we take the derivative of this binomial raised to the power k, the k is going to come down. K over k factorial goes to k minus 1 quantity factorial. And the power on the binomial goes down by 1. But don't forget that there's a chain rule, and when you put the derivative with respect to t on x, you get 0, and the derivative with respect to t on negative t is going to give you negative 1. So that's this first term, letting the derivative hit the binomial to the power k. And then the other term, we're just using the product rule, says that the kth derivative, throw on one more derivative, is going to give you the k plus first derivative. Okay, so not too bad there. And we want to use this side computation to aid us in computing the derivative of g. G is a function of t. Taking a derivative of g with respect to t means that this constant f of x under derivative with respect to t will go away, but that this term, negative f of t, will turn into negative f prime of t. For the next term, it takes the form of this side computation that we did and will produce, by the product rule, two terms. Note that there is an existing negative on the term, and this first term will introduce a second negative, and thus this binomial goes to 1, and we come up with positive f prime of t. And then here's the form of the second term. That f prime will turn into f double prime on the binomial. Good. And we do that until we get out to the nth derivative on the binomial to the power n to produce this last pairing. Very nice. And then putting a derivative on the very last term, since it's a derivative with respect to t, our n of x is a constant, x minus a is a constant. We only have to differentiate the binomial to the power n plus 1. N plus 1 comes down. The minus goes to plus, since we have a derivative with respect to t on x minus g. All right. Well, we're going to get a wonderful payoff right now, since as we peruse back over our work, we notice that there is lots of wonderful pairings that provide a beautiful telescoping effect, where a term appears with both a positive 1 coefficient and a negative 1 coefficient, meaning that they go away, and the only terms that do not pair up are the very last two terms. So that this g prime of t, after the telescoping effect, is simply the last two terms. All right. So remember earlier back, we were able to show that this function g agrees with itself at both a and x, that they were both 0. That here we've computed the derivative, and therefore g is differentiable. And by being differential, it's continuous. And that these from Calc 1 are the conditions under which we may appeal to Rolle's theorem. And that Rolle's theorem says that somewhere between these endpoints and x, you can find a point c such that the derivative at that c is 0. Hey, hey, hey. So let's make that statement. In other words, g prime at c will become 0. Then this right-hand side swap out for t being c and set it equal to 0. All right, so remember the big question. Does the Taylor series converge to the function? And that the remainder is the function minus the nth Taylor polynomial. And here we're discussing Taylor's theorem with remainder. So this is our star of the moment, the nth remainder. As we have this set equal to 0, we can solve for the nth remainder. Now, the form of the nth remainder is familiar yet different. It's familiar because we're coming up with an nth derivative evaluated somewhere over that same number of derivatives, quantity factorial, and the binomial x minus the center to that same power. But there's a big difference that typically the nth coefficient would be evaluated would be found by evaluating the derivative at A, the center. And here, this is a C, not A. So we don't know exactly what the C is. We do know that the C depends upon the N. That makes things a little bit tricky. And we're actually going to do something that is typical of analysis. We're going to swap out this precise equality, which dominates algebra, in favor of an inequality. So we know that there must be a C, but we don't know what the C is. We know that the C is going to come from the interval I. So perhaps instead what we'll do is we'll say, well, if we can gain control over this numerator, in other words, if that numerator, the size of it, hence the absolute value, can be controlled by something everywhere in the interval, then for sure it's going to control the derivative at this, I don't know what it is, C. So while we're coming up with this precise form of the nth remainder, we actually are using it only as a stepping stone to come up with this estimate. And it's the estimate, this imprecise form, rather than the precise form, which gives the better information. Okay, so this is what we wanted to come to. This is Taylor's theorem with remainder. We have an assumption that we have a good function n+1 derivatives on an interval I, which contains the center, and that the notation of Pn is the nth Taylor polynomial to allow us to define the nth remainder. Then we know that we can find a C in between an x and an a, such that the nth remainder takes this form, but like we just noted, that really what we care about is that we get a remainder on, we get an estimate on the remainder. Okay, so let's see if we can use this. So that you might get a little bit more familiar, something like radical x, radical of 9 is 3, but what about radical of 10? You've used a calculator before. You know how to use the calculator to compute rad 10. Well, the calculator has to do some work. How do you know that it's good? Well, here you want to investigate finding that the nth remainder gets small. All right. So we have Taylor's theorem with remainder, and we want to use it to answer our big question. Do Taylor series converge to the original function? Okay, so this was the big question. Does the Taylor series for f at a converge to the function f? Okay. Well, the quick answer is that we have convergence if and only if the limit of the remainder goes to 0 everywhere on the interval. If that's the case, then we get that the Taylor series converges to the function everywhere on the interval. All right, so let's investigate this. Okay, so let's come back to the exponential e to the x. The nth Maclaurin polynomial takes a very simple form. Since e is its own derivative, e to the 0 is 1. We always get a numerator of 1. Placed over I factorial as coefficient to x to the I. Now, including all powers, 1 over n factorial, x to the n, all powers, that is the Maclaurin series for e to the x. Does this p sub n converge to e to the x? P sub n, taking its limit, will be this Maclaurin series. Does this exactly represent e to the x? That's the big question. The Taylor's theorem for remainder requires an interval of convergence, We know to compute the interval of convergence is to appeal to the ratio test. Let's look at the next term divided by the current term, or times the reciprocal of the current term. We produce a nice cancellation on the factorials as well as the exponential. N plus 1 quantity factorial below n factorial leaves you with n plus 1. N plus 1 copies of absolute x in the numerator over n copies in the bottom leaves you with 1 copy in the top. We're looking for n to go out to infinity. Thus, the ratio test is going to give us that rho, the limit is 0, which means that the interval of convergence is the entire real line. So this Taylor series, Maclaurin series, at any x is going to represent a value, but is that value exactly the same thing as what you would produce by plugging into e to the x? That's the big question. All right. So the Taylor theorem for remainder is requiring that we come up with an estimate on the remainder. To come up with that estimate, let's pick anywhere in the interval of convergence. So pick some positive b, and then we have an interval about 0. 0 is the center. And then pick a point in this interval, negative b to b. Well, the derivative of e to the x is just e to the x. And since e to the x is an increasing function, e to the x anywhere in this interval will be controlled by e to the b, the right-hand side, the right endpoint. Let that be m. And then we need to show that m over n plus 1 quantity factorial on absolute of x raised to the n plus 1 goes to 0. Well, we know that this Maclaurin series converges. We have its interval of convergence. And thus, by the divergence test, we get that absolute of x to the n over n factorial must limit to 0. And then by properties of limits, multiplying that by m is still going to limit to 0. And that shows what we need. That the nth remainder goes to 0 as n goes to infinity. Okay, that's it. By Taylor's theorem for remainder, we've come up with r sub n going to 0, which means that the Taylor series for e to the x converges to e to the x. Another way to make that statement is to put an equal sign between the two expressions. And this is happening everywhere in the interval of convergence. This is happening everywhere on the real line. All right. So this is an example of that, an answer to that big question. Does the Taylor series converge to the function? In this case, yes. Okay. Here's a nice little assignment, a little review to express out the functions f and g to find their Maclaurin series. And a little hint to that is to recall what we've done in the past. Something like 1 over 1 minus x, we reference the geometric series to come up with its power series representation. Something like ln of 1 plus x, we used term-by-term integration to come up with its power series representation. And then now here, we've used the Taylor's theorem with remainder to come up with the Maclaurin series representation for e to the x. All right, good. So, using Taylor's theorem, we found the Maclaurin series representing e to the x converges to e to the x. Let's see if we can do the same thing for sine of x. Remember that sine, when you sketch it, goes through the origin, is an odd function. And thus its Maclaurin polynomial, its Maclaurin series, is made up of only odd indexed terms. The even indexed terms are all 0. Knowing the Maclaurin polynomial allows you to easily write down the Maclaurin series. You trivially have to change out n to infinity, and you're done. But the big question is, does this expression provide the exact same value as sine of x does when you plug in x's taken from the interval of convergence? Well, what is the interval of convergence? That's easy. You go do the ratio test. The next term times the reciprocal of the current term. The factorials will cancel out nicely. Except in this case, we have plus 3 underneath plus 1. That means there's a plus 3 and a plus 2 until you get down to plus 1. So you come up with a product of two terms. That in the numerator, again, that plus 3 means that it's 2 more than the plus 1. So you end up with 2 copies of the absolute of x. But as we're letting I go out to infinity, the I grows in the bottom, meaning that rho will be 0. And the interval of convergence is going to be, again, the entire real line. Knowing the interval of convergence, you then move on to trying to control the nth remainder. To control the nth remainder means coming up with an estimate on the derivative. Since we're working with sine, sine's derivative is cosine, and cosine goes back to sine plus or minus. And that both sine and cosine never produce values bigger than 1. So their absolute value will always be less than or equal to 1. And as e to the x takes this form, we know that x in absolute raised to a power over that power quantity factorial will tend to 0 as the power goes out to infinity. Okay, so we're getting, once again, that the Maclaurin series does in fact converge to the function. In other words, we can write the function and put an equal sign down and then write down its Maclaurin series. Extremely nice. Extremely nice. All right, to make sure everything is sitting nicely inside of your head, take some time to repeat, showing that the Maclaurin series for cosine converges to cosine everywhere on the real line. Okay, and that brings us to the end of the video. Thank you so much for watching. Please like and subscribe if this is useful to you, and I will see you on the next one.